Hello, in this session we're going to discuss masonry shear wall design. My name is Sam Rubenzer. I am the founder of Force Consulting and the managing director. I'm a licensed structural engineer in the state of Illinois and a professional engineer in many Midwestern states. I have my engineering degree from the University of Minnesota and an MBA from Marquette University. Here at Force we have a lot of different masonry design experiences. We've been consultants to the masonry industry for the last 15 years. And we often create papers and presentations such as this, sharing our knowledge of masonry design. In this presentation, we are going to explore different types of shear walls. We're going to build a little bit of knowledge about the shear wall design best practice. We're going to look at different ways to make shear walls more effective and maybe overall building design more effective. And then we'll also review some tips for modeling shear walls with software. First and foremost, before we get too far, it's always important to remind ourselves the strength of masonry. Here with shear wall design, we know that strength of masonry is going to be a really important aspect of the overall design. If we can justify and utilize higher strength materials, certainly that can lead to a more efficient design and a lot of different masonry shear wall design applications. We also know that we have to select a mortar and grout that's going to be compatible to the overall strength of masonry, FRMM, that we do select. So let's go ahead and get started in discussing shear walls. So FRMM, why is it so important? So there's a lot of different reasons, but making sure that we have an efficient and effective shear wall design is certainly going to be one of the many reasons why we need to understand and utilize the appropriate FRMM strength of masonry for our project. We know based on the masonry code, TMS 402, that a wall is going to be any element that's 3 times longer than it is thick. So an 8-inch thick element, 24 inches long, will be considered a wall. We also know that a load-bearing wall would have loads greater than 200 pounds per foot in addition to self-weight. From that, shear walls, we have different definitions for masonry shear walls, especially as it pertains to seismic design. We have ordinary, detailed, unreinforced masonry shear walls that we can consider. Then we also have ordinary, intermediate, and specially reinforced masonry shear walls with different design values. Here you can see some different response modification factors, deflection amplification factors, and different allowable seismic design categories for the different types of reinforced masonry shear walls. So going from the detailing that would be required for an ordinary reinforced shear wall to an intermediate to a special certainly is going to have different seismic load implications as we go through our design. We also know that partition walls are not shear walls, so we do talk often in different videos about the partition wall design, making sure that we do understand that partition walls are not shear walls and shouldn't be detailed that way. Should be much lighter and simpler elements. If you do size them as shear walls, we definitely know that they're going to get more complicated and a lot more reinforcement. So we definitely want to make sure that we don't have any of these, anything like this going on for partition walls. We definitely want to make sure that they're efficient elements. Getting to the different seismic wall characteristics, we know that for ordinary reinforced masonry shear walls, we have different detailing requirements that are going to be there for our reinforcement. We know that we need at least a number 4 vertical reinforcement within 16 inches of the edge of the opening and within the last 8 inches of the wall. We know that we have joint reinforcement needed at least at 16 inches on center or number 4 bar at 10 feet on center horizontally. Reinforcement at the top and bottom of openings greater than or equal to 16 inches and extend 24 inches past the edge of the opening, but not less than 40 times the diameter of the bar. Reinforcement within the top 16 inches of the walls, and then certainly based on one of the different design methodologies of ASD or strength design. For intermediate reinforced masonry shear walls, which again gives us a higher response modification factor, so a lower overall seismic design force, a more ductile response. All that we require once we go to that step is to make sure that our vertical reinforcement is no further apart than 48 inches on center. You see, because the ordinary reinforced masonry shear walls, really the reinforcement can be much further apart than 48 inches on center. I've seen certainly designs at 6 feet or 8 feet on center for ordinary reinforced masonry shear walls. But if we want the higher response modification factor, higher ductile performance, we know that we need to tighten up that vertical reinforcement a little bit. And then if we go to especially reinforced masonry shear walls, there's a lot more requirements that we can maybe cover a little bit towards the end of the session. For the most part, we're going to cover some of the requirements for the low to moderate seismic designs in the ordinary and intermediate. But we definitely will cover the special reinforced provisions in later videos. We know that for masonry design, we discussed within the different design of masonry design sections that the concrete masonry, similar to concrete, likes vertical load. So the more vertical load that we can put in, the more compression stresses that we can create within our masonry elements. Any lateral forces are going to create some tensile and compression coupling forces and shear stresses within our design elements. We also know that when we have a material like concrete masonry that's very good in compression, not so good in tension, the best way to maybe increase the overall capacity of that element is to add some reinforcement that is good both in tension and compression. But here we can add some minimal reinforcement elements that are good in tension, that form a force couple that creates a very strong element for moment and bending resistance. So again, reinforced masonry, we know that adding in those reinforcement elements is going to increase the overall capacity. We can see here some of the different equations that have been determined for the nominal axial and flexural strength for our concrete reinforced masonry elements. We can see an axial force allowance for members with an H/R not greater than 99. So if it's not too slender, we can use the first equation, equation 9-13, or if we have a height to R ratio of greater than 99, if we get a little bit more slender, we know that we have a higher reduction value of 70 R over H squared. So we know that equation 9-14 would be more applicable in that situation. Further on in the code, we can see different requirements for shear. If we're dealing with concrete masonry shear walls, we know that we have a certain component of the shear that is determined by just the concrete masonry elements. So VNM would be the shear value of just the masonry elements, or VNS in equation 9-15 would be the contribution from the steel reinforcement. We don't need to always add additional steel reinforcement to our concrete masonry shear walls. We certainly may have enough capacity with just the masonry, but you can see that equation is going to be what we need for determining the overall capacity. We know that when we have a higher moment to shear times the length of the shear wall, if that's a higher ratio, that we have a little bit lower capacity. So here you can see equation 9-16 going to be the shear capacity of 6 times the overall net area times square root of the masonry strength, F'(m), times the gamma G. So that's going to be our value, and then that's going to be dropping down once the moment divided by shear times the length goes above 1.0. We know that we can interpolate between those different values. And so then we can certainly determine the overall capacity. And then you can see also the gamma G is going to be equal to 0.7 for partially grouted walls and 1 otherwise. Next, looking at just the specific masonry contribution for the shear, you can see the equation 9-18. On the right side, you can see V and M giving us a nominal shear capacity for just the concrete masonry component. We then could see equation 9-19 for the additional steel shear capacity, 0.5 times AV over S times Fy yield strength of the steel times dV. So again, just kind of summarizing what some of the different moment capacities would be for the different elements. We can see the ultimate force that the factored moment and demand that we have on our overall walls. We can see what that value is going to be for Pu divided by Ag less than or equal to 0.2 times F prime M. And then if the H over T, if it gets a little bit thinner, it's going to be dropping down to 0.05 F prime M. Looking at what the actual force kind of diagram would look like for the in-plane shear capacity, you can see that we have reinforcement that would have contributing factors to the tensile forces that we can create for the overall section. We know that the concrete masonry is going to be the compression element at one end that's going to be resisting that kind of force couple. We know that the overall net compressive strength is going to be the compression minus the tension. We know that the overall moment capacity is going to be that sum of the F times Y. Basically looking at the overall section and seeing where the reinforcement is relative to the compression block. The axial moment curve is certainly a very good curve to learn and understand that when we have pure flexure, we have a certain moment capacity when we have zero axial force. We also know that we have pure compression, which would be the overall axial force if we have zero moment. And then you can see the curve of the balance between the two. Things that we can learn from the curve is if we add axial force, you can see that beyond pure flexure, you can actually increase the overall moment capacity by adding an axial force. To a certain point, there's a balance point to where that you start to lose some moment capacity once you add more axial force. And once we understand some of those different values, we can certainly learn a lot about what the different capabilities and capacities would be for our concrete masonry shear walls. So bending moment goes up if we add in some gravity loads. Again, looking at these diagrams, certainly the high lateral bending forces, anytime that you create some tension forces, adding in loads certainly going to reduce some of the tensile demands and the overall force that you have. We know that we adding in the reinforcement is going to be internal tensile forces because the masonry is going to crack. We're going to lose that tensile stress at the far edge because the masonry is going to crack. We know that the reinforcement internally to the wall is then going to start to develop some internal forces to create that internal force couple. So again, masonry very good in compression. Adding in the reinforcement does give us a lot more capacity for moment, and then concrete and steel being both components that we can utilize for developing shear capacity. Some of the other provisions within the TMS code, we know that we don't want vertical reinforcement any further than 8 feet apart or 96 inches, which is going to be, so for the ordinary reinforced masonry shear walls, we know that we basically have an upper limit of 96 inches on center for our vertical reinforcement. We know that if we have an intermediate wall, that drops in half down to 48 inches on center. Maximum reinforcement, we need to not consider when you consider special boundary provisions, but you do have a maximum reinforcement for the overall section. We have flexural and axial strength that's defined. We have vertical reinforcement that we don't want less than 1/3 of the horizontal reinforcement, and nominal shear strength that would be defined by the code. Different types of walls, how to make shear walls more effective, and then just some different software examples that we want to look at. Different types of walls. Again, we can't have an unreinforced concrete masonry shear wall. Again, if we can keep everything in compression, if we have more vertical load and stresses than we have lateral forces. Now, this can happen if there's a high amount of vertical load for certain, but it also can happen if the lateral load or the in-plane shear force is fairly minimal relative to the weight of the wall. So good examples might be a big box retail store where we have much length of wall and pretty low shear per foot in the in-plane demand. Other examples would be obviously multi-story buildings where we have a lot of load bearing that can increase the overall gravity forces to keep the, again, in-plane shear force relatively low. So again, unreinforced could be possible, but we know a little bit of reinforcement goes a long way. So most of the projects that I have ever been involved with are all going to be looking at some amount of reinforcement. Hybrid projects are also projects that we get involved with quite a bit, where there's a steel frame and then the masonry shear wall is going to be internal. There's also concrete hybrid designs where we have a concrete frame and masonry. We also have perforated shear walls where you're going to basically have just a wall that's going to have an opening in the middle of it, and that's going to be just fine with the right tools. We're going to be able to do a good analysis and design. And then lastly, wall groups. We know that anytime that we can bring together many different walls, we create an overall composite section that's going to have a lot more capacity. So we highly encourage that as well. So yes, you can certainly do unreinforced. Again, if we have enough axial force, that can certainly benefit. Masonry is good at compression. We've said that before. Steel does add quite a bit more tensile capacity, so it definitely increases the overall capacity very quickly. Just as a very simple example, looking at some different loads on different unreinforced versus reinforced wall. If we have a 24-foot long wall, 18 feet high, we have 1 kip per foot of dead load, 0.3 kips per foot of in-plane wind load. I can look at the overall design. Ungrouted, unreinforced, the load to capacity ratio is 0.85. So it technically works for the unreinforced section. Moment's going to be controlling. So the moment equations are going to be what give us our overall demand. If we add just simply, a couple bars at the end and a couple within the interior portion of the wall, so a number 5 at 120, you can see the load to capacity ratio drops from 0.85 down to 0.5. So same wall, almost the exact same materials, just a little bit of reinforcement and grout. You can also see the shear is going to be the controlling portion of the equations for the walls. So certainly if we look at the two designs, I think definitely the one on the right, slight cost increase with the number 5 bars that you would have to have in the design and a little bit more grout is going to give us a much more capacity for that design. Hybrid designs, looking at hybrid designs, it's simply going to be a frame that's going to be built, and a lot of times it's going to be a constructor-led decision where the contractor wants to go with the all-steel erection, so steel columns and beams and floor members all at once, and then the sequence of adding in masonry would be after the fact. So again, if that's the overall construction sequence, certainly a hybrid design can work pretty well because maybe the masonry is there for multiple reasons, architecturally and structurally. We can still utilize the shear wall capabilities and sometimes the load-bearing capabilities of masonry when we look at a hybrid design. So we shouldn't see this. These are just different examples of steel braces within masonry wall plane. Again, there's just no need for it. The masonry is going to have just as much or more capacity than the steel element. So I think it's really good to understand what the masonry capacity would be, how to connect the steel elements to masonry to utilize, because the fact of the matter is all of the elements are going to be more expensive. The masonry is going to be more expensive. The steel is going to be obviously more expensive because it's there and it doesn't need to be. So all of the elements are more expensive in this design. We certainly want to take that steel out, utilize the full capacity of our masonry elements, and make sure that we have them connected. So here you can see a quick illustration of a steel beam with the bent plates down to the masonry wall. Certainly that connection is going to be important, and we discussed that in other sessions, but looking at the overall aspect of the steel element having some in-plane force or axial force in that steel member that we're trying to get into a concrete masonry shear wall below. So we're going to be kind of combining the best properties of both here. There's going to be a type 1 hybrid design. So doing a type 1 hybrid design is going to be looking at the shear capabilities of masonry, but there's going to be gaps left on each side to the columns or to the beam above. Really, this is going to be a pretty contractor friendly construction. We're going to be able to build with nominal, say, heights for masonry elements. Maybe we don't even have to cut them to fit them within this frame, which can be certainly contractor friendly. Leaving that little bit of gap at the top is going to make building the masonry wall easier. But what we do is we do leave some capacity on the table, because the masonry wall does have a lot of vertical load bearing capabilities. And if you remember back a few slides, if we add in some of those vertical loads, we actually increase the overall shear wall capabilities of the masonry wall as well. So there's got to be a little bit of give and take here. Sometimes it's going to be better to build tight to the underside of steel so that you can get that gravity load in there, get a little bit more capacity out of your system, out of both your vertical load carrying capabilities of the masonry, then take some of the burden off of the steel, but you actually make the shear wall even more effective often in those designs. And so what is that? That's going to be a type 2 hybrid design, where we actually build up tight to the underside of the steel. Again, that can be a little bit of more difficult construction. Oftentimes we're going to be cutting the masonry elements to fit within that space, grouting those elements to, again, close the gap between the top of the masonry wall and the steel elements that you have there. So type 2 hybrid is definitely going to be a better overall material solution. Again, it's going to take a little bit longer to build. A little bit more construction is going to need to be involved, but type 2 hybrid is going to be a very good use of materials. There's also a little bit of nuance here. Type 2A is going to be using tension tie downs for overturning, not necessarily looking at the elements in terms of how can we create some tension tie downs. Does it have to be doweled bars into the foundation, or maybe it's going to be a hybrid design that's sitting on a steel frame, so it's going to be welded rebar down to the steel frame below to be able to create this type 2 hybrid design. There's also type 2B that doesn't rely on any tension, just allow some compression to be created both from the masonry into the steel above and the masonry to the steel below. So certainly as that steel frame tries to rack, we have some compression that is used to develop some of that couple force and transfer some of the forces. So again, type 2A, 2B, a little bit of difference in some of the connections that are made to the different surrounding elements. Using some of the different software tools that we have available, we know that if we were going to build in these masonry shear walls, we need to be able to model walls and model all the different materials for that walls. 3 different programs that we recommend here: Tekla Structural Designer, RISA 3D, RAM Elements. All are different programs that give a little bit of a focus to the masonry material so that we can get the right elements modeled within the frames. Certainly we needed them modeled in the steel members. And then there's some connectivity. Some of the different software programs have differences here within the RAM Elements programs. There's actually interfaces to define the type 1, type 2A, and 2B interfaces between those steel elements and masonry walls. There's actually a type 3 where you would build the masonry tight all the way around. That isn't really codified and well supported, but it's certainly there and available and options for your design. You could certainly do this also in RISA, which I show here, or Tekla Structural Designer. You just have to build your own custom links to be able to support the type 1, type 2A, 2B, type 3A, or 3B for the design. Just a few notes on movement joints. Again, we have an entire session on movement joints of masonry, but just talking a little bit about movement joints and what the overall impact is on shear wall design. Certainly putting in movement joints, putting too many in, too close together, I call it, would be adding one more joint maybe than would be necessary, which would weaken the in-plane capacity of the masonry shear wall. So again, that's a really important aspect to recognize. Again, looking at, adding one more joint might be seen as, well, that's a responsible thing for the contractor to do. He wants to make sure the wall doesn't have any cracks in it. But what he doesn't maybe realize is adding that one more joint is going to weaken the in-plane shear capacity of your masonry walls. So certainly from an overturning bending capacity, it's going to have a very similar shear capacity, but an overturning bending capacity is going to be a lot less. But certainly putting movement joints too far apart, you'd have cracks in the wall. We don't want to have that. So we definitely need to have a good understanding and a good balance on the design. So here, just kind of looking really quickly at some long walls versus short walls. Again, 3 24-foot long walls, which would be the same overall length as 4 18-foot long walls. Again, looking at what some of the different capabilities would be for the forces. For the long walls, I would have about a 33% increase in the shear that would be able to be developed with the longer walls. Again, just one example, but we certainly have more capacity when we have longer walls, less capacity when we have shorter walls, and all kinds of different varieties of conditions that could create some of these differences. But again, movement joints is really important, where they're located, how they're located within the overall design. Longer walls are going to be better than shorter walls. Perforated shear walls, again, we have a lot of good architects that are adding openings for their clients, so that those openings are going to be within our masonry walls, which is great. But what we utilize now today is more perforated shear walls, which is going to allow the overall capacity, again, of the design to go up. It does require a little bit more effort, I think, on the analysis side, and so we'll talk about that here as well. But you definitely, again, movement joints, do not want to have them located at openings. It's definitely going to give us a significant loss in the overall length of the potential walls, at least maybe 2 feet beyond the edge. Again, there's nothing in the code. That's just a guide that I use for locating movement joints at least 2 feet away from the edge of the openings to make sure that we can develop arching action and all kinds of stuff for lintel design, but also for the shear wall design. We want to make sure that we have a robust section on each side of the opening to design. So again, perforated walls, software tools do give us a lot of options for perforated walls. In RISA, in RAM, and in Tekla, Structural Designer, all different softwares are going to have the same capabilities of modeling a larger wall panel and then adding in an opening area that's going to remove some of the wall panel from that area. You can have plate elements that are then going to be able to represent what the overall model would be. So perforated shear wall is going to look like this. You're going to have different regions that you're going to be able to analyze and see what the forces are for those different regions. Now, obviously, putting this within a finite element analysis program is very nice because all the different interfaces between those regions are going to have some balance that you're going to have to determine and understand. So the lintel in region 2 is going to then be connected to regions 1 and 4. Region 3 is also going to provide a lot of stiffness in connecting both 1 and 4 and below the opening. So really it does provide a much more robust, a lot more capacity in the overall design than if we had different individual walls. So perforated shear walls look just like this. Again, getting those movement joints away from the openings, which is an absolute anytime that you have reinforced concrete masonry walls. You want to have those openings away from, those joints away from the openings, and it has very large impacts on the actual shear wall capabilities for the wall. So again, if you had an unreinforced wall, that again was where you can put the joint at the opening, but once we have the reinforced wall, we want to see that the joints away from the openings. So again, looking at an elevation like this, historically, we maybe would have broken the wall down into different continuous wall segments. We have different software tools that even look at this walls this way today, but it's certainly going to be diminishing the overall value of what you could use by just having larger panels that are perforated shear walls. So again, this is going to take a finite element analysis software to really understand and appreciate, what the forces are between those lintel areas, those areas above the openings, to the jamb areas on each side of the openings, to the area below windows, or just how those different elements are going to be connected to the foundation. There is quite a bit of complexity in those plate elements that we have to account for, and so certainly utilizing the right tools for our shear wall analysis and design would be necessary. This is an example that we also looked at within the movement joints, again looking at the shear capacity of this overall section. Having joints that would be put within those jambs would be very much detrimental to the overall shear load capacity. So again, moving those joints away, having a long elevation where we have continuous reinforcement is certainly going to have a much higher in-plane shear capacity for this design. Certainly you can go back to the areas outside of the openings. If you're in a lower seismic area, it's probably beneficial to go back to the large walls. The shear capacity is going to be fine for a large wall without any openings, but elevations with a lot of repetitive openings can benefit from moving those joints away and utilizing continuous lintels and a much better in-plane shear capacity due to really having basically a moment frame versus wall elements. So looking at the overall analysis, if we looked at a couple short walls on each side of the opening, so two 8-foot walls, as opposed to the two 8-foot walls plus the wall connected in between. If I just look at the overall capacity in a perforated shear wall versus two individual walls, you can see in this example I had about 3 times the overall capacity of the multiple short walls. So using perforated shear walls is definitely going to give us a lot more capacity. Now again, back to an example of maybe a big box retail store, maybe that's not that important. Maybe we can just use individual wall panels and just not necessarily consider perforated shear walls. But there's going to be plenty of projects where we work on where maybe the only masonry is a stair and elevator shaft with several openings. Making sure that we keep a perforated shear wall in those shaft walls is going to be adding a lot more capacity and stiffness than having multiple short walls in an elevation. So again, this is going to have about 1/3 the capacity of this in my one example. Now certainly different height to length aspect ratios can certainly change the overall, but the point is you have a lot more capacity when you have a perforated shear wall than if you do not. Certainly, again, the finite element analysis is going to be necessary. Looking at the lintel is going to have a lot of contribution in the in-plane direction. You're going to have load reversals for your in-plane shear if it's going to be a reversing in-plane load. A lot of wind load, seismic loads, obviously you're going to operate in both directions. So recognizing that you have positive, negative forces at the top and the bottom of the lintel areas. Certainly, again, a finite element analysis can help you determine what those forces are going to be for that area above the opening so that we can get a proper lintel design. A few more notes on the overall lintel. Again, we have an entire section on masonry lintels that we can look at masonry lintel design and construction as well, but just the lintel contribution to the in-plane shear design is certainly going to be really important to understand what the overall forces are going to be for those elements as they connect to these shear walls on each side. So again, just to look at the overall wall performance, we can look at, again, finite element analysis to look at, see what, adding in openings really doesn't change the overall stress, the maximum stress areas on these taller walls. You can see that the openings certainly are there, but the stress concentrations aren't that much different. If I start to isolate these elements, you can see actually much higher stress forces in these designs, you can see at least a 50 or 100% increase on the overall stresses. You're going to see a lot higher deflected shape. So you do lose a lot of capacity anytime that you would put a joint, say at an opening or at both sides of the opening, and create individual towers instead of an overall perforated shear wall. And the same would go for the shorter, longer design. Again, the stress goes up significantly between the two, almost 300% of the stresses that you would have in this example. Other suggestions for lateral capacity, looking at, again, those stair and elevator shafts that I mentioned before. Certainly perforated shear walls is going to be really important, but also keeping the walls together. Having them be continuous around the corners is going to be really important. Boxed wall groups is what I would call a shaft wall, that all of the walls are going to be interconnected to one another. Those have, in this example, we just crunched some numbers to determine what the overall load to capacity ratio would be for different walls that are separated. We have a load to capacity ratio of 1.33. If I simply just connect those walls together, keep all of the construction the same strength of masonry, the same thickness of our masonry elements, same reinforcement that I'm using in both cases, and I can see my load to capacity ratio is about half that design. So again, box wall groups is going to be a great way to add in capacity for shear walls, perforated shear walls. You know, all of that stuff coming into play here with some of these shaft wall designs. Again, capacity of boxed wall groups is certainly going to be really important anytime we have multi-story buildings, 2 to 12 stories with masonry. Masonry wall groups can be very effective and comparable to what you'd have for a concrete wall design. Now, certainly looking at these concrete masonry elements, looking at, you know, maybe different strength of masonries as we get into some of these taller projects as well. You know, maybe we need an F''M of 4,000 for the lower levels of this design, and maybe we need and can just utilize 2,500 or 2,000 at the top few floors for the design. So again, just looking at these, again, shaft walls, you know, this is a project that I looked at many years ago, and you could see that I was doing just what I mentioned before, changing and recognizing the strength of masonry, but then also the reinforcement in those shaft walls as we go up the 6 stories of this building. And just one last example here before we wrap up, we're just going to look at a reinforced load-bearing shear wall, some axial force, shear forces, and moments that you have on the wall. This example comes out of the Masonry Designer's Guide 2016. You're going to see for this shear wall, we're going to develop that axial to moment curve to kind of see what the pure bending, the pure compression forces would be, see where the actual balance point is going to be for the design, so we can see what the overall capacities would be for shear moment and axial forces. So here you can see shear capacity is going to be determined from the moment and shears and the overall length of the shear wall that we have considered. So there's no need to check the Vmax per 402 since the shear force is resisted by just the masonry. We can use prescriptive horizontal reinforcement. Must be designed as an intermediate reinforced shear wall because we used an R value of 3.5. So certainly you could change the R value, go to just an intermediate reinforced masonry shear wall, but then certainly that's going to change some of the different loads for the design. So certainly we can look at the design. We can do the design checks by hand. We can also go into software. We can see very similar axial to moment curves that are going to be created for the design and do a nice little comparison between our hand calcs and what we have in here from finite element analysis. And one last example for the shear walls, again, just looking at some of the different reinforcement that you would have for this wall, F''M of 2,500, 16 feet tall, 24 feet long. We have vertical reinforcement of number 5s at 96 inches. Center, just joint reinforcement at 16 inches. Looking at the wall, a non-load bearing wall, no out of plane force. We can see the in-plane load of 2.5 kips per foot. We have an interaction equation of 1.42. If I simply make that a load bearing wall, add some vertical load of 2 kips per foot of dead load, we can see that the same in-plane shear force is going to bring our interaction equation down to 0.613. Our axial check is only at 8%, so we know we have a lot of axial capacity. We can vary this. We can kind of see what happens if we add a lot more vertical load. And again, this is just a study. Obviously, you just kind of have one set of forces that you're designing for. So you can see the 5 kips per foot brings our interaction to the same value, axial check of 0.17. 20,000 pounds per foot, we can see that's when our axial check is going to get to about 15% over capacity. So we can certainly add in too much axial force for the actual strength of masonry. Certainly in a situation like that you had a lot of axial force, maybe the increase of the F'(m) would be necessary for designing that element in those loads. Again, we have different software programs. We have a few different sessions on some of the different software that's available for doing shear wall design, masonry, direct design, quick masonry, and TEDS are all different software programs that we utilize here at Force, certainly in doing shear wall designs. And the Tekla Structural Designer, RISA Floor, RISA 3D, RAM Elements program, all having very good tools for masonry design and shear wall design in them as well. Here's a couple different images where you can see masonry working pretty hard in some of these buildings for shaft walls. Again, you can see these perforated shear walls and wall groups going a long ways for the design, whether it's steel or wood buildings, or just a large concrete masonry building where you can see multiple shaft walls going up for the design. So in conclusion, you can see that you have a lot of different options for concrete masonry shear walls. You have unreinforced, which again, we don't utilize too much in new walls, but we certainly switch to lightly reinforced to intermediate reinforced walls where we start to have reinforcement closer together to all the way to specially reinforced masonry shear walls. Hybrid designs are certainly things that we could evaluate. Perforated shear walls, wall groups are all ways to add more capacity in for our masonry elements. Utilizing the right tools for the design, we certainly can get a very accurate analysis and efficient design for our masonry shear walls. So with that, we'll go ahead and wrap up. I appreciate all of your attention today. If you have any questions, please reach out. Thank you.